Okay, welcome back. Hopefully you had a nice break. We're going to continue on here, and I think we're on chapter 8. Last time in chapter 8, we started talking about kind of two really important sort of conversion factors, and one probably a little bit more important than the other. But we talked about the mole. And remember that the mole is abbreviated MOL. Again, without the E, it is a mole. Again, it is not a molecule. And in chemistry, when you say you have a mole of something, it does represent a certain amount of whatever it may be. And that is Avogadro's number 6.022 times 10 to the 23. Remember, though, as we talked about with Avogadro's number, the units that are associated with it does change depending on sort of what you're using. They can be atoms. They could also be molecules. They really can be kind of any units that you want. Atoms and molecules, obviously, being the most common sort of units you'll probably come across when you're using Avogadro's number. But really, this is again just a conversion factor. You could sort of write two conversion factors. You could put a mole up on top and Avogadro's number on the bottom. Or you can flip it around and do Avogadro's number up on top and a mole on the bottom. And really, this is our conversion factor to go between units of moles and either atoms or molecules or backwards. So Avogadro's number is really sort of the conversion factor to go either way. And remember that you should not use Avogadro's number in every case. If there is really no mention of atoms, molecules, or anything like that, then you really should just leave Avogadro's number alone and not use it. Probably the next sort of conversion factor that we really talked about, which is probably the most important one, is the molar mass. And the molar mass has units of grams per mole. We get that from the periodic table. It again is the number that's on the bottom, which, as we talked about last time, is numerically equal to the AMU per atom sort of atomic mass that we talked about earlier on in a previous chapter, maybe in this chapter we talked about it. We do use molar mass because, again, it gives us sort of a more usable unit, like grams are involved in it. So if you had something like hydrogen and 1 mole of hydrogen, there would be 1.008 grams of hydrogen. That also is really just a conversion factor. You could say in 1.008 grams of hydrogen, there's a mole, or you could flip it around and put the mole up on top, 1.008 grams. Molar mass is definitely our conversion factor to go from grams to moles, which is a super common conversion, or backwards there. Moles back to grams. Thank you. So, in addition, you could apply sort of molar mass to things that are sort of compounds as well, or molecules. So, if you had something again like water and you wanted the molar mass of it, again, all you're basically going to do is just add up all the parts. So, there are two hydrogens, each at 1.008 grams per mole from the periodic table. You look at oxygen, there's basically one oxygen there times 16 grams per mole, which is what you see under oxygen when you look there. And that gives us, again, 18.02 grams per mole as the molar mass there of water. So if it's something that's more of a molecule or something like that, you basically add up all the parts. The general rule for molar mass is that we go to about 4 significant figures, is essentially what we go to when we pull it off the periodic table, and in general, when we just calculate the molar mass of something, usually about 4 significant figures is sort of where we round it to. And once again, with Avogadro's number, you could also use it as a molecule as well. So if you had 1 mole of hydrogen, that would have 6.022 times 10 to the 23 atoms of hydrogen. Again, though, if you're talking about water, 1 mole water would be 6.022 times 10 to the 23 molecules of water. And again, that's where we sort of change the units. We're doing something, again, that's not just an element by itself, which would be considered an atom. Any questions on that there from last time? All right, so I think where we laid up was maybe some examples. So why don't we do some examples here, I think. All right, so why don't you try this one here? How many moles of helium are there in 5.46 grams of helium? Okay, so taking a look at this one here, we're looking for moles and we have grams. So again, one of the first things you want to think about is obviously you do not need Avogadro's number here. The reason you don't need Avogadro's number here, again, there's no mention of molecules, there's no mention of atoms. This is again just a conversion between grams to moles. And always that conversion is the periodic table and the molar mass conversion that you get it. So you would go to the periodic table, once again, look up helium, and that would basically tell you that there is 4.003 grams per mole is the molar mass of helium. Once again, you should think of molar mass as just a conversion factor, which means, again, if you just want to think about a dimensional analysis way, you could flip this conversion factor if you needed to, like so. And that's the approach that I would take in terms of the calculation. 5.46 grams of helium. Once again, opposites cancel, so grams are on top. I would need to use it in sort of the flip version over here. And that's going to give me moles of helium, 4.003 grams. Again, setting it up like this, we know we're multiplying the top still, we're dividing the bottom. Grams are going to cancel, and that's going to get us a 1.36 moles of helium. In terms of significant figures, the original number here is probably what you want to look at, as the molar mass should probably be considered more of a exact sort of conversion. That's where we work at. Any questions on that one there? Okay, let's take a look at a few more here. Why don't you try this one? What is the mass in grams of one gold atom? Okay, so on this one, the key word to look for here is I do see atom. So that sort of wording there in the problem definitely tells me somewhere along the way I do need to use Avogadro's number. I am going in this case from atoms to grams. And really, the unit that kind of ties both of those together is moles in the middle. So, sort of the process here is I could use Avogadro's number to go from atoms to moles. And once I have that, now that's a conversion from moles to grams. And once again, I can use my molar mass as my conversion to do that. So, in this case, we do know that 1 mole of gold would equal 6.022 times 10 to the 23 atoms of gold. Again, Avogadro's number. We also know from the periodic table here that the molar mass of gold is 197 grams per mole, which again, we could use either way as a conversion factor. So we essentially got everything that we need here. We're going to start with one gold atom, and again, just use dimensional analysis here to help us cancel everything out. Once again, if it helps, you can put it over 1. That should tell you that atoms are on top, and I need to get rid of them by putting it in the opposite location. So my Avogadro's number here with atoms are going to go in the bottom location there to cancel. And 1 mole of gold will go on top. Once again, multiplying the top, dividing the bottom, the atoms are going to cancel. If I stop the calculation right at this point, we're units of moles of gold, which is close to what we want. But once again, we do want grams. So I could continue on again because I set it up like dimensional analysis. I can see moles of gold are up on top. Opposite location to cancel. Gonna make me choose my conversion factor over here on the left. 197 grams per mole of gold. still multiplying the top and dividing the bottom, so moles are going to cancel. That leaves us just grams left over, which is good because that is the unit we're looking for. So we're basically going to take just 197 and divide it by Avogadro's number, making sure to use our exponent button for sure. And we're going to end up with a 3.271 times 10 to the minus 22 grams of gold, which is a very small number considering we're talking about one individual gold atom in this case. First off, any questions on the calculation here? Again, in terms of significant figures on this particular one, since one gold atom would be probably considered something as an exact number, something you would count, you really could probably lay up as many significant figures as you want. So I went with 4 based off of the molar mass in this particular case. Yeah. Other questions about that? Okay. All right, so let's try this one. How many grams of zinc are there in 0.256 moles of zinc? Zinc 6538 looks like. All right, so in this one, we're looking for grams, and we have 0.256. Remember, as I mentioned earlier, MOL is again moles. It is not molecules. Yeah. So because there is no mention of molecules or atoms, this again is a conversion between moles to grams. And once again, that is the molar mass from the periodic table that allows us to do that conversion. And again, we go there and grab off what we need. And we would have 6538 grams per mole as our molar mass. Once again, we could also flip it upside down if we needed to in our calculation. Here we're going to start with 0.256 moles of zinc. Once again, the moles of zinc are up on top, so we actually do just need to use it the way it is. And we could go 6538 grams per mole of zinc. Still multiplying and dividing here. Moles are going to cancel. Going to get us here 0.256 times 6538. Going to go 16.7 grams of zinc in this particular case. So once again, as I mentioned last time, definitely in chemistry, if they are talking about molecules, they typically will write out the word molecules. So again, if you see that MOL, it is definitely an abbreviation for moles and not molecules or anything like that. Any questions on that calculation there? All right, let's try a couple more here. How many moles are there in 23.2 grams of ethanol? And how many molecules are there in the same amount? Couple information might be helpful. Carbon 12.01 from the periodic table, hydrogen 1.008, and oxygen 16. So once again, this is just a grams to mole conversion, so that should always just trigger the molar mass there from the periodic table. So in this case, we just need to add up all the parts. So for our C2H6O, there are 2 carbons, each at 12.01 from the periodic table, plus 6 hydrogens, each at 1.008 from the periodic table, and 1 oxygen, that is 16 from the periodic table. So again, just using our molar masses there. Adding all that together is going to give us the molar mass of this particular molecule. Looks like we're going to go 4607. Again, about 4 significant figures is typically where you go with molar mass. And remember, this is really just our conversion factor that we can use like it is with grams on top, moles on the bottom, or we can also flip it if we need to. So doing this first part of the calculation here, 23.2 grams. Once again, grams are on top, so in this case, we do need to kind of flip our molar mass and put the grams in the opposite location on the bottom and moles up on top here so that everything properly cancels out. So when we multiply and divide, our grams will cancel. And in this particular case, we will end up with here. I'm going to round since we are looking for an answer here. And I'm going to go about 3 sig figs based off the original number, and that's 0.504, it looks like. First off, any question on that part of the calculation there? Now that we actually have it, except that is moles, not grams. Put the right unit in there would be good. Moles there. Um, so now that we do have it in moles, the next part of the question basically is how many molecules that would be. So we're going to take it now from moles to molecules. And remember, that's the key word there, molecules. That should then tell you Avogadro's number should be involved in this particular case. Once again, Avogadro's number is always the same. 1 mole is 6.022 times 10 to the 23. Here we are going to use molecules, as this is a molecule. And we'll start with our number there, 0.504 moles of C2H6O. Once again, opposites to cancel. So we do want moles on the bottom. So we'll go 1 mole. And Avogadro's number here will go up on top. And that would be our molecules in this case. Again, the moles are going to cancel. I'm going to actually use the whole number here for my calculator, not the rounded number of the 0.504. So I'm just going to use the whole number in my calculator, 6.022, 23. And that's going to look like a 303 to the 23, it looks like. 3.03 times 10 to the 23. And those are molecules here of our C2H6O in this particular case. A question on that calculation there. So a reminder, if you set it up dimensional analysis, multiply top, divide the bottom, opposites canceled. It's a good way to kind of think about these conversions along the way. Any questions on those there? All right, one last one here maybe. What is the mass in grams of 1 molecule of caffeine? And again, some numbers here, 12.01 for carbon. Hydrogen still 1.008. Oxygen 16. And our friend nitrogen 1401. Somewhere along the way, we are starting with molecules, and we do want to end up at grams. Once again, as I mentioned earlier, the moles is basically what kind of ties those two units together. So here we will use Avogadro's number here again to go to moles, and at that point, molar mass from the periodic table to kind of take it the rest of the way. So might as well calculate the molar mass here of our formula. There are 8 carbons, each at 12.01 from the periodic table. There are 10 hydrogens, 1.008 from the periodic table. 4 nitrogens, 1401 from the periodic table. And 2 oxygens, each at 16 grams per mole. If we do all that, looking like 194.2, I think, is our molar mass. And again, grams per mole. We also have, obviously, Avogadro's number always. 1 mole of this here will equal 6.022 times 10 to the 23. Here we will use molecules, as this is a molecule rather than an atom by itself. And that's what we're going to start with. So we'll go our 1 molecule here of C8H10N4O2. Again, molecules are up on top, so opposite location to cancel. That means Avogadro's number will go on the bottom here to cancel. And that's a mole of our C8H10N4O2. At this point, our molecules will cancel. We have moles up on top, and now we've already done this conversion. We're ready to roll with this one. Taking our molar mass, we got to cancel out the moles. So moles up on top, opposite to cancel, 194.2 grams on the bottom. Moles are going to cancel. And if we do that, they're going to end up with 194.2 divided by 6.022 to the 23. End up with here about 3.225 times 10 to the minus 22 grams of this guy here. Any questions on that calculation? So again, you should be able to obviously convert grams to moles, moles grams, into atoms and molecules, but definitely that molar mass conversion used a lot in chemistry. Any questions on that there? And obviously multiplying still across the top there, dividing what's on the bottom. All right, one last thing here before we kind of move on from this, and this is sort of another sort of conversion that you will maybe sometimes come across. And let's talk about actually that here. So maybe we'll just use the one that we used here. So let's say here, C2H60. And let's just say that we did have, and we'll borrow those numbers actually, 23.2 grams of it. And we want to know how many grams of carbon would that be? All right, so in this particular case, we are looking for how many grams of carbon that would be. And carbon obviously is not the entire thing here, which is C2H60. And that means along the way, we do need a conversion factor to go from kind of the whole thing to just carbon. And we can actually get that conversion factor from the formula itself. So when we look at the subscripts here, and even obviously the one that's not written there, these can be considered moles of each of those elements. So from the actual formula, we could have several conversion factors that we could use from it. We could say in 1 mole of the entire thing, there would be 2 moles of carbon, and that 2 is basically right there. We could also say in 1 mole of the entire thing, there is 6 moles of just hydrogen. And last, we could say in 1 mole of the entire thing, there are 1 mole of oxygen. So we could actually use the formula itself as a conversion factor to go from like the whole thing to one of the elements involved, which is actually what we need here, right? Because at some point we got to go from whole thing to just the carbon. Now, in order to use these relationships here, as you can see, they are all mole to mole relationships, which means your original number here does need to be converted into moles. So that would be the first thing that you would want to do. And just to save time, we did that on the previous problem. We would need to convert it to moles. I'm just going to steal that answer we used on the previous problem, which is right here, 0.504 moles of C2H6 there. So we'll borrow that there. So we did that earlier, 0.504 moles of C2H6O, obviously using the molar mass to do that conversion, just like we did in that example earlier. Now that we have it in moles of the entire thing, that's where we can now just pick up the calculation. And since we are interested in carbon by itself, we can use this as a conversion factor. Still same idea, opposites cancel. Moles of the whole thing's up on top, so 1 mole of the whole thing on the bottom to cancel, and 2 moles of carbon. And that is what's going to allow us to go from, again, the whole thing here to just moles of carbon. If you were interested in moles of carbon, you actually would have an answer at this point, and your answer would be 1.008 moles of just carbon. But we're not interested in just moles of carbon. We're actually interested in grams. So what we have here again is a mole to gram conversion. And that again is the molar mass from the periodic table that's going to allow us to do that. As we saw in a couple of the earlier examples, carbon on the periodic table here is 12.01, which gives us 12.01 grams per mole. So to finish out this calculation, and I think I will actually just erase what I just wrote there and just do it right here. The moles will cancel. Again, we want moles of carbon in the opposite location, which would mean on the bottom, and the grams up on top. And again, the moles of just carbon would cancel, and we would end up with about 12.1 grams of carbon in this particular case. If I could write 1 there instead of 0, that would be good. So sometimes you may be asked, maybe not about the whole entire compound. You may be asked about just like a element within that compound. And you could actually, again, use the formula itself as a conversion factor, a kind of mole to mole conversion factor, where the subscripts represent how many moles you have of each element, and allows you to go from the whole thing to each individual thing. Any questions on that calculation? Obviously, here, if I was interested in hydrogen and oxygen, I could do the similar calculation, obviously using the relationship between hydrogen and oxygen and the whole thing there. Any questions on that there? Okay. All right, so let us continue on then. Next thing we're going to talk about is formulas and a couple of different types of formulas. And we're going to talk about the molecular formula. A molecule, as we know, is a basic definition that basically you need at least two atoms together. As we talked about before, a molecule could be two atoms of the same or two or more of the same, or it could be two or more different elements coming together. But this is a basic definition. Remember, a compound does need to have two or more different elements involved in order for it to be a compound. A chemical formula, as we just saw, expresses how many of each of those atoms, of those elements you have in a compound. Now, the molecular formula does tell us really the exact number of atoms of each element in a molecule. So if you have the molecular formula, it tells you exactly how many of everybody that is there. The simplest types of molecules are those diatomic molecules, things like oxygen, which is O2, nitrogen, any of the halogens, right? Fluorine, chlorine, bromine, they all come as twos. Now, sometimes formulas, molecular formulas, give you some information about how it's sort of connected, and sometimes it doesn't. It just tells you basically what is present. Very common one, for example, here is ethanol, as we just saw in that previous example. The formula for ethanol, C2H6O. But sometimes people will write the formula for ethanol as CH3CH2OH. If you count up all the elements on each of those things, you have two carbons, you got six hydrogens, and one oxygen. They both represent the same thing. The difference, though, in the formula is sometimes people will give you what's sometimes referred to as the structural molecular formula, which gives you some information about how it's sort of connected. And that would be more this one right here. This gives you some information about how ethanol is put together. If you were to draw sort of like a Lewis structure here for ethanol, it would actually look something like this. And thus you can see how you probably get to that formula here. This is CH3, CH3. Then you have obviously the CH2 next to it, CH2, CH2, and then lastly you have obviously the OH there, and the OH, right, and the OH. So obviously the one on the right gives you a lot more sort of structural information about how it is put together. The one on the left is just like that's what's there basically is these sort of three elements, and it really doesn't kind of indicate how it's maybe put together. So that's very common in sort of formulas or molecular formulas. A lot of times people will include more of a kind of structural information, and sometimes they'll just give you the basics of these are the elements that are present. Any questions on that there? Now, the empirical formula, like that experiment before spring break, is basically the simplest whole number ratio of what elements are present. So the empirical formula basically tells you the simplest ratio of what is present. not necessarily exactly how many of everybody that's there. So if you take our hydrogen peroxide example here, when we look at the molecular formula, it is basically 2 hydrogens for every 2 oxygens in this case. And that can be reduced down by a whole number to 1 hydrogen and 1 oxygen, which would give us our empirical formula of HO. So if you have a molecular formula and you look at the bottom subscripts and you can reduce down everybody and still have a whole number, and that's the important part, those subscripts on the bottom do need to be whole numbers. You could do that, and that would get you your empirical formula. It's basically the whole number ratio of what's present. All ionic compounds are empirical formulas. So when you think about an ionic compound, positive guy, negative guy, put it together in the simplest way to get to zero, that always gives you a empirical formula when you put those together. Now, sometimes the molecular formula and the empirical formula are the same. So if you had water, that is the molecular formula. That is 2 hydrogens for every 1 oxygen. There is no way to reduce that down anymore and still have whole numbers. And water would be both the molecular formula and the empirical formula would be the same because it is as simple as you could get it. So it is possible for them both to basically be the same in this particular case. We take another example here, hydrazine N2H4. That is 2 nitrogens for every 4 hydrogens. If you reduce this down by 2, that's the same as 1 nitrogen for every 2 hydrogens. That would give us our empirical formula here of NH2 on the reduction there. As I mentioned just a second ago with water, sometimes they will be the same. If you have something like NH3 as well, you cannot reduce that down any further. 1 nitrogen, 3 hydrogens is as simple as you could get. And as I mentioned before, always ionic compounds are always empirical formulas. They are the simplest whole number ratio of what is present. Any questions on that there? Yep. No, it is still the chemical. So the sort of reason there's sort of an empirical formula is um, it is the simplest one, for example, that you can kind of figure out in a laboratory. So, like the experiment that was before spring break, you could do a very simple experiment where you just kind of weigh grams and heat things up, and you can figure out the empirical formula first. Is kind of the simplest thing that you can figure out in a laboratory. But ultimately, it's still the same thing, but it just gives you that simplest ratio of what's present. So it's a useful formula in that sense. Other questions? All right. And here is a couple other examples there again of things that both the empirical formula and the molecular formula obviously will be the same, as you cannot reduce down any of these guys and still end up with this whole numbers for everybody. For every 2 hydrogens, obviously you reduce everybody down by 2, and that would get you a 1 carbon for every 1 hydrogen, and that would get you an empirical formula here of CH. For our second one here, we got 2 iodines for every 5 oxygens. That is as low as you could go and still have whole numbers. Obviously, you can't reduce down and still have those whole numbers. So this would also be its empirical formula in this case. And lastly here, this is 6 carbons for 12 hydrogens and 6 oxygens. You could reduce everybody down here by 6 here, I think, and still hit some whole numbers. That's going to give you 1 carbon for 2 hydrogens and 1 oxygen. So that'll get you CH2O here would be our empirical formulas. Any questions on that there? Okay. So if you do have the formula for the molecular formula, you can just simply reduce it down and that will get you your empirical formula. Let's talk about another important aspect of this, and this is what's known as percent composition by mass. And percent composition by mass, that should be multiplying, I think, is basically found by taking the mass of the element you're interested in. So the percent composition is the mass of the element in the formula divided by the molar mass of the compound, and you times it by 100%. So take the mass of each individual element within that compound and divide it by the molar mass of the entire thing, times it by 100, and that'll give you, for example, like the percentage of carbon or the percentage of hydrogen within a formula or the percentage of nitrogen. Obviously, if you add up all the percentages of each of the elements, they should equal 100%, right? That way you have the entire compound there. If they don't, then that's problematic along the way, if they don't add up to 100%. So let's take a look at one here and sort of take a look here. We have hydrogen peroxide, and we want the percent composition of both hydrogen and oxygen. So the first thing that we would want to do is get the molar mass here. So 2 times 1.008 for our 2 hydrogens, plus 2 times 16 for our 2 oxygens. And that's going to get us here 3402, we'll call it. So to figure out the percentage of hydrogen here, we're going to take the mass of hydrogen in the compound, which is 2 times 1.008 grams per mole, or 2.016 grams. We're going to divide it by the molar mass of the entire compound, 3402, and we're going to times it by 100% in this case. And that will get us here about 5.926% hydrogen. We could do the same calculation for oxygen in this case. In this case, we have 2 times 16 for our 2 oxygens that are present, or 32 grams, divided by 3402 grams per mole, also times 100%. And that will get us here 32 divided by 34.02 times 100%, about 9406 here percent oxygen. So we can see definitely this is made up by mass. Mainly oxygen is the higher one. When I add up those 2 percentages, that is essentially 100%, and that's good, right? They should, again, add up to 100%. By the way, I could have also avoided the second calculation because these are the only 2 elements involved. So you could have took 100 minus 5.926, and that would have got you the percentage of the other element as well. So because these are only 2, for the second one, you could have done 100 minus the first percentage as well. Any questions on that one there? All right, so why don't you try the next one here? How about the empirical formula of HO? What is the percentage of hydrogen and the percentage of oxygen? So take a moment there and calculate it up. Let's take a look. So this is really the empirical formula here for the last one, the H2O2. And we're going to do the same thing. We'll get our molar mass. We're just basically going to add that together. So 16 plus 1.008. That's going to give us a molar mass here, 1701 grams per mole. And for our percentage of hydrogen in this case, since we have just one hydrogen, 1.008 grams per mole up on top, divided by our molar mass, 1701 grams per mole, times 100% here, going to give us our percentage here for hydrogen, 5.926. And we'll do the same thing here for our oxygen. We have just one oxygen in this formula here, 16 grams per mole divided by 1701 grams per mole times 100%. And we will see here by punching the right number. That'll be good. 94.06, I believe. Percent oxygen. So when we look at the percentages by mass of the hydrogen and oxygen of the empirical formula here versus the actual molecular formula, we do see that they are the same. And that is because, again, the empirical formula is just the simplest whole number ratio of what's present. So your mass to mass ratio on each of them are going to be the same, and you'll end up with the same percentage. So you can't calculate the percent composition of each element from the empirical formula or the molecular formula, and they will come out the same, again, because they're based on the same sort of ratio of each of the elements to one another. Any questions on that there? One last one here. Percent composition of each of these elements here in phosphoric acid. Again, hydrogen 1.008, phosphorus 3097, and oxygen. Okay, so let's take a look since we're getting to the end here. Obviously, we're doing our percent composition, so we're going to get our molar mass here first. So there are 3 hydrogens, 1.008 grams per mole. There's 1 phosphorus, 3097 grams per mole, and 4 oxygens there, 4 times 16 grams per mole. That's going to give us a molar mass here of 97.99 grams per mole. Again, we'll do our percentage of hydrogen. There are 3 of them, again, at 1.008 grams per mole in the formula, divided by the molar mass of the entire thing, and times 100%. That's going to get us here. Looks like 3.086 grams, 3.086% of hydrogen. We'll do our percentage of phosphorus next. There's just 1, so 3097 molar mass of phosphorus divided by 97.99 grams per mole times 100%. That's going to get us 30.97 divided by 97.99 times 100. Looks like 3161. Now, at this point, you do have 2 of the 3. You could add those percentages together and actually subtract from 100 and get the last one. Or you could just do the calculation here. And in this case, we have 4 oxygens at 16 divided by 97.99 and times 100% in this case. And that's going to get us 4 times 16 divided by 97.99 times 100. About 65.31, I think. 31% here. And again, if you add all those up, we should be at about 100% for each of the elements present. Any questions on how to calculate percent composition by mass? Okay. All right, we're going to lay it up for now.